For the beam loaded as shown by area moment method, determine the slope and deflection at points A, C, and D. EI is constant. So here is the situation. So this time, you may select E as the moment center so that you don't need to compute for reaction at B, but since it will involve so many areas, so let's just select D as the moment center and let's compute for the reactions at B and at E. Actually, if I were to solve this, I will not compute for the reactions anymore because I know the moment at E from moment at E without drawing the moment diagram, shear and moment diagrams. Then from there, I can compute the reaction at E also. But as beginners or those who are not yet expert on moment diagram by parts or moments without computing for the reactions, so let's just compute for the reactions. So moment E equals 0, clockwise positive, let's assume, or upward reaction at B, horizontal reaction is 0. So we have equals By times 12, then minus 15 times 14, minus 25 times 5, 2.5 plus 4 is 6.5. So 25 times 5 times 6.5. So ME is, By is equal to 2045 over 24 kilonewtons. Then moment B 0. So we have RE times 12 equals RE times 12 plus 15 times 2. Then minus 25 times 5, 2.5 plus 3 is 5.5. So 25 times 5 times 5.5. RE is equal to 1315 over 24 kilonewtons. So from there, because we select D as the moment center, this is 1315 over 24 EI. So let's have the moment of the loading first. 25 times 5 times 2.5, this is second degree, is equal to 312.5 over EI. Then moment due to 15, 15 times 10 is 150 over EI. Then here we have 15 times 2, so 30 over EI. At C, 15 times 5, 75 over EI. Then here 30 over ER, 15 times 2. Then moment due to the reaction at B, 2045 over 24 times 8. So we'll divide the area into two triangles later. So 2045 over 24 times 8 is 2045 over 3 EI. Then 1315 over 24 times 4. This is 2045 over 8 EI. 2045 over 24 times 3 is 2045 over 8 EI. Then this is 1315 over 24 times 4 is 1315 over 6 EI. So this is the moment diagram by parts. So let's compute deviation of E relative to the tangent at B. So it is 0.5 of 8 times 2045 over 3 EI. This distance is 8/3 plus 4 because our moment, we are computing deviation of E relative to the tangent at B. So the moment arm of the centroid of this triangle from E is 8/3, 1/3 of 8 plus 4. Then plus this area, 0.5 of 4, 1315 over 6, moment arm 2/3 of 4 or 8/3. Minus this spandrel, 1/3 of 5, times 312.5 quantity 5/4. This is 5 over 4. 5 over n plus 2, so 5 over 4 plus 4. We compute the moment of the area from E. So the moment arm should be from E. Then this small triangle, the distance of the centroid from D is 2/3 of 8, 16/3, then plus 4. So minus 0.5 of 8 times 30 times 16/3 plus 4. 2/3 of 8 plus 4. That's it. Then minus for this big triangle, 0.5 of 8 times 150. This is 8/3, 1/3 of 8 plus 4. So 0.5 of 8 times 150 times 8/3 plus 4. So calculating using your calculator, deviation of E relative to the tangent at B is equal to 275815 over 24 EI. It is positive, so E is above the reference tangent at B, as shown in the figure. And that's it. So this is theta B. This is also theta B. Theta B is negative because it is sloping down to the right, or the tangent is below the positive x-axis. So computing for theta B, it is negative of 275815 over 24 EI divided by 12, because that's 12 meters, 3 plus 5 plus 4. So theta B is negative 957.691 over EI in decimal form. So let's concentrate first on AB. Let's compute theta A and deflection at A. So EI, division of A relative to the tangent at B, is equal to moment of area between A and B. There is only one area, and this is the area. 0.5 of 2 times 30 over EI. Then its centroid from A, because this is division of A relative to the tangent at B, is 2/3 of 2, which is 4/3. So again, 0.5 of 2 times negative 30. This is negative below the horizontal. Then moment arm is 2/3 of 2, so 4/3. Division of A relative to the tangent at B, therefore, is negative 40 over EI. So let's enlarge this, magnify this portion so that we can analyze it well. So this is the tangent at B, this tangent here. This is the expected elastic curve, because point A on the elastic curve should be below the reference tangent, because it is negative. Division of A relative to the tangent at B is negative, so negative 40 over EI. So this is it. Division of A relative to the tangent at B, negative. So point A on the elastic curve is below the reference tangent at B. Therefore, deflection at A is above the horizontal axis of the beam. Therefore, it is positive. The distance of the point on the reference tangent to point A on the beam is, because this is 2 meters and that is theta B, so the entire distance is 2 times theta B. And this is the deflection at A, which is expected positive. From the figure, delta A is positive of absolute value of 2 theta B minus absolute value of deviation of A relative to the tangent at B, which is negative 40 over EI. And since we already computed theta B, we can now compute delta A. Likewise, let's compute the rotation between the tangents at A and the tangent at B. Because the area is negative, so it is negative. So this is the tangent at A. Because theta AB is less in magnitude compared to theta B. Theta B is 900 plus. So it will be sloping downward also. EI theta AB is this area, 0.5 of 2 times negative 30. So it is negative 30 over EI. The negative sign indicates that the tangent at A to the tangent at B is clockwise, as shown in this figure. So the tangent at A to the tangent at B is clockwise. It is sloping downward because theta AB is small compared to theta B. So therefore, from the horizontal drawn through the point on the elastic curve to the tangent at A, that's theta A. From the horizontal to the tangent at B, that's theta B. From the horizontal to the tangent at A, that's theta A. So theta A is below the positive x-axis, so it is negative. And geometrically, it is negative of absolute value of theta B minus absolute value of theta AB. That's theta A. Theta A, negative of absolute value of theta B, which is negative 957.691 over EI, minus the absolute value of theta AB, which is negative 30 over EI, which is that. So therefore, theta A is negative 927.691 over EI. So that's also the answer to theta A by double integration method in example 100E. Then from the figure, delta A is positive of absolute value of 2 theta B minus deviation of A relative to the tangent at B, which we already computed. So therefore, delta A is positive 2 times theta A minus deviation of A relative to the tangent at B, absolute value, so minus negative 40 over EI. So delta A is equal to positive 1875.382 over EI. Then let's have the elastic curve first. So let's magnify this part here, 3 meters. Let's consider B and C. And let's magnify it so that we can analyze it well, and we can compute. Let's magnify the figure so that you won't be confused. It's easy to explain. So this is the tangent at B. This is point C. The distance between B and C is 3 meters. You look at the figure here, and you also look at the areas between B and C that must be considered. This is the tangent at B, so that's why that's theta B. So EI theta BC is the area between B and C. So 0.5 of 3 times 2045 over 8 minus, so this is trapezoidal. Let's divide the trapezoid into 2 triangles, one with height 30 and the other with height 75. So minus, for the smaller triangle, minus 0.5 of 3 times 30. Then for the bigger triangle, minus 0.5 of 3 times 75. So theta BC is equal to 3615 over 16 EI. In decimal, this is lesser than theta B. So that means the tangent at C is sloping downward as shown. And the angle between the tangent at B to that tangent at C is theta BC. And the rotation is counterclockwise, that's why theta BC is positive. This is the line through C on the elastic curve horizontal line. So this is theta BC, positive, because the rotation from the tangent at B to the tangent at C is counterclockwise. From tangent at B to the horizontal, that's theta B. And therefore, from the tangent at C to the horizontal, because the tangent at C is below the horizontal, below the positive x-axis, so theta C is negative. And theta C is negative of absolute value of theta B first minus theta BC. So theta C is negative of absolute value of theta B, which is negative 957.691, minus theta BC, which is 3615 over 16 EI. So theta C is negative 731.754 over EI. So for the deflection at C, let's have it on the next slide. So let's have the magnified figure between B and C to analyze delta C. So this is deviation of C relative to the tangent at B, which is expected positive. The distance from C on the beam to the point on the reference tangent is 3 times theta B, because that's 3 meters. And this is the deflection at C, which is expected negative because point C on the elastic curve is below the horizontal axis of the beam. So that's delta C. So from the figure, delta C is negative of absolute value of 3 times theta B minus absolute value of deviation of C relative to the tangent at B. So computing for deviation of C relative to the tangent at B, EI deviation of C relative to the tangent at B is equal to 0.5 times 3 times 2045 over 8 EI. Moment arm is 1/3 of 3 is 1. So this is trapezoid. So considering the small area first, minus 0.5 of 3 times 30 over EI, then 2/3 of 3 is 2 meters. Distance of centroid from C is 2/3 of 3, so 2 meters. For this bigger triangle, minus 0.5 of 3 times 75, 1/3 of 3 is 1. So deviation of C relative to the tangent at B is equal to positive 2895 over 16 EI. So that delta C is negative of 3 times absolute value of theta B. Absolute value of 3 times theta B is theta B minus deviation, absolute value of deviation of C relative to the tangent at B, which is 2895 over 16. Expressing delta C in decimal, delta C is negative 2692.136 over EI. Then, there's no need to magnify portion CD, so we have a space here. So let's evaluate AI theta BD. It is area between B and D. So 0.5 of 8 times 2045 over 3 minus area of spandrel, 1/3 of 5 times 312.5, then minus area of trapezoid, but we'll divide the trapezoid into these two triangular areas. 0.5 of 8 times 30 minus 0.5 of 8 times 30, then minus 0.5 of 8 times 150. So that when we evaluate deviation of point D relative, this one, relative to the tangent at B, we just copy these areas and include the location of centroids from D. So evaluating theta BD is 8915 over 6 EI, approximately 1485.833 over EI, which is greater in magnitude than theta B, which is 957.691 over EI. So it means that the tangent at D is sloping up. It is above the horizontal because theta BD is greater than theta B in magnitude. So that's theta BD. This is theta B. So the tangent at D is above the horizontal, so it is positive. And this is theta D, which is positive of absolute value of theta BD minus absolute value of theta B. So theta D is absolute value of theta BD minus absolute value of theta B. So theta D in decimal is equal to 528.142 over EI. So you compare this with the answer to example 100E. by double integration method. Then let's evaluate this deviation of D relative to the tangent at B. The distance from the reference tangent to the beam is 8 times theta B, because the distance from B to D is 8 meters, so 8 times theta B, and this is the deflection at D. So the deflection at D is negative of absolute value of 8 theta B minus absolute value of deviation of D relative to the tangent at B. So let's evaluate deviation of EI, deviation of D relative to the tangent at B. So let's copy this area, 0.58 2045 over 3 times 8 thirds. So the moment arm is from the centroid of the area to D, because this is deviation of D relative to the tangent at B. Then minus this area, then this distance is 5/4. So the moment arm is 5/4. 1/3 5, 312.5 times 5/4. Copy this area, minus 0.5 of 8 times 30. Then 2/3 of 8 is 16/3. The moment arm is 16/3. Then copy this area, minus 0.5, 8, 150. The moment arm is just 8/3. 0.5 times 8 times 150 times 8/3. So computing for deviation of D relative to the tangent at B, it is equal to positive 331.5365 over 72 EI. So finally, delta D is negative of absolute value of 8 theta B minus absolute value of 315.365 over 72 EI. Expressing delta D in decimal, delta D is negative 3281.459 over EI. So that's it for this problem.